Hello, fellow Algebra 2ers. Here is your video key for your Unit 3 exam review. First, we have rewrite each expression in exponential form. And so remember, when you have a root, the root is the denominator of a fractional exponent, and the power that you see here is your numerator. So you can see that on 16, 17, and 18, all kind of the same problem, really. Just knowing what a fractional exponent means, essentially. Okay, on 19, simplify. So we're looking for perfect square factors of 50, which 25 is one of those. So now you can split 50 into 25 times 2, but we know the square root of 25 is 5. We don't know the square root of 2, so it stays under a square root. Now when you have a different root, in this case a cube root, you're going to do the same thing, except instead of looking for perfect square factors like we did here, we need a perfect cube factor. So 27 is a perfect cube, and 54 is 27 times 2. So now you can cube root the 27 and turn it into 3, and the cube root of 2 we don't know, so it stays as cube root of 2. So similar thing as up here. We'll do the same thing over here. To be able to actually add these two things together, the numbers under the roots have to be the same, otherwise they won't be like terms. So you find a perfect fourth factor of 32, which is 16, and of 162, which is 81. The fourth root of 16 is 2. The fourth root of 81 is 3. But these, we don't know the fourth root of 2, so they stay fourth root of 2. And now you have 2 plus 3 is 5. And so you have 5 fourth root of radical 2. Just like when you add like 2x plus 3x, you get 5x. Same thing happens here. This just stays the same, kind of like a variable would. 22, this number was changed on the key here. I think it was a 5 to begin with. So if you leave it as a 5, this problem just isn't doable, because in the end, you can see how we simplify the cube root of 250 with cube root of 125, which you know is 5. But then this is a 2, and this would be a 5 on the original problem, in which case you would just stop here. Again, this would be a 5, and there's nothing you can do. But if we change this to a 2, now we can actually add these together at the end and get that. So whichever way you did it is fine. Simplify each expression. So we're just, when you multiply two numbers that have the same base, you add the exponents. So the only thing tricky here would be adding fractions, but you get a calculator. You should have access to Desmos on your test. So you just add 1/5 and 3/10, and that's your new exponent. On 24, we subtract the two exponents, which is what we're showing here. Again, you get a calculator, so you don't even have to worry about the actual process of adding or subtracting fractions. 25, this is what we call power to a power. Now be careful on 25, because this is where this kind of gets distributed to both of these things. So it's 16 to the 1/2, which means square root, so 4. And then these get multiplied together because it's power to a power, so you get y to the 4th. Same thing is going on 26. We have a 1/3 power, which means cube root. So you cube root 64, which gives us 4. You cube root 125, which gives us 5. And you can multiply these exponents together, which gets you 1. Here's some intermediate work that you don't necessarily have to show, but that's where it comes from, just raising all things to the 1/3 power. All right, so some simplifying here. Again, we're taking 1,250 and finding a perfect fourth factor, which is 625, because the fourth root of 625 is 5. We don't know the fourth root of 2, so that stays there. Now the x to the 8th, probably the easiest way to think about this is split up x to the 8th. We know out of fourth root things that are to the 4th power. So if you split up x to the 8th into x to the 4th times x to the 4th, you can fourth root both of these separately and get x for both of them. And so you get x times x on the outside with nothing underneath, and x times x is x squared. That's where that comes from. So that's how you want to do all of these. So this one, we want everything to be perfect cubes. We do know the cube root of 27 already is 3, but take f to the 6th and make it f cubed times f cubed. G to the 9th is g cubed, g cubed, g cubed, and h to the 4th is h cubed times h. And so we can cube root the two f cubes and get f squared. We have 3 of these, so that's why it's g cubed there, because it's g when you cube root them all. Remember, we're actually cube rooting all this stuff. And then you can cube root this h, which is right here, but this one we can't cube root because it only has a power of 1. So that one stays underneath. And that's where that answer comes from. On 29, similar thing here. So we know the fourth root of 16 is 2. This can be, a to the 7th can be written as a to the 4th times a cubed. This was split into 2 different fourth roots, but you can keep it all under the same fourth root when you do the problem. So like a to the 4th, a cubed is right there, and then b to the 8th, b to the 1st. Except b to the 8th, I would actually probably make it b to the 4th. So let's get rid of this 8th here. The way I explained it earlier is like this. I would make it b to the 4th, b to the 4th, and then we have one more b. And we went to the 4th because we're fourth rooting. So the fourth root of 16 is 2. The fourth root of a to the 4th is a. And then we have this a cubed left over, which is still under the fourth root. We have 2 different b to the 4ths, which get multiplied when you fourth root them, so b squared, and this b stays underneath. Okay. On 30, we just have some functions that are defined right here as f and g, and then you just do f plus g, which is combining like terms, so you just add or subtract the coefficients here. So 5 plus negative 2 is 3. We multiply the 2 together, so you multiply the numbers, add your exponents, so that's where 2/3 came from. And now we're dividing, but when you divide, you have common factors on top and bottom of x to the 1/3, so it's just negative 5/2. On 33, again, 2 different functions here. Find f of 2, that just means plug 2 in up here, you can see that work. G of negative 7 means take negative 7 and plug it in for that x right there, which is what this is showing. 35, f of g of 2. So find g of 2 first. Take 2, plug it into here, and we get 12. And then find f of 12, which is what's being shown right here. And you can see that simplification there. And then same thing is going on in 36 with g of negative 1. Or sorry, f of g of negative 1. Take negative 1, plug it into g, get an answer, and then take negative 3 and plug it into f. Notice the use of parentheses right there when we plugged in a negative number, because a negative 3 squared will be a positive 9. That's a common mistake. So you can't type it on Desmos without these parentheses or you're going to get it wrong. Okay, we got graphs. Parent function is square root of x. This is just kind of for your own use. Hopefully you know those points. But square root of x here is our parent function with those points. And then we're just going to go left 4, up 6. So that's the blue one. And the purple one is right 1. So we've moved this point right 1. And then all the y values on the parent function get doubled. And so this was at a y value of 1. It moved right and then doubled. This was at a y value of 2. It moved right and then doubled to 4. This was at 3. Moved right 1 and doubled to 6. And then similar things here with cube roots. So here's our parent function. Again, in dash black right here. You should know what that looks like. And then this is just going to go right 2, up 5. So that's the red one. So we'll take this point and go right 2, up 5, which is right there. So you do that with all the points. And this one is just the parent function stretched by 3. So take all your y values and triple them. So 0, 0 stays at 0, but this is at 1, becomes 3. This is at 2, becomes 6. And you can do that in the other direction also. And now we have inverse functions. Are these inverses? Remember, definition of an inverse, the easiest way to explain it is all your x and y values switch. So look at all your data points here and see if everything switches. Over here, we have 1, 10. Even though all of our x's that were here are over here, it should be, if it's 1, 10 here, it should be 10, 1, but it's not, so they are not inverses. And then graphically, you're looking for a reflection over the line y equals x. So those are inverses. Here's the line y equals x. These are not reflections over the line y equals x, so they are not inverses. And then we have some solving here. Remember, before you can solve a square root equation, you need to get the square root by itself, or any root for that matter. So add 12 first, then you can square both sides, and then solve from there, which I'll let you just look at that solving. It turns it into an algebra 1 equation. Since this is a cube root, you cube both sides, cancels the cube root on this side, cube this number, solve from there. These can have extraneous solutions, so you really should check. Here we have a square root on both sides, so you can either square both sides or just know that what's underneath has to be equal to each other, which is how we talked about in class. And then same thing with this one. You have two different fourth roots are equal to each other, so just set what's underneath equal to each other. Or raise both sides to the fourth power. And that's it. Hopefully that's helpful.